This is Physics 2211, Lab 4, Oscillations by William Barron. The purpose of this lab is to examine the motion of a spring mass system in which the spring mass swings in an arc while also oscillating on the spring. The expected results are that the total energy is constant throughout the experiment and that the tracker data and computational model data don't differ too much. The fundamental physics principles used were Newton's second law, where F equals delta P over delta T, where we can derive the position update and velocity update formula shown on the right. The energy principle, which says that the system's change in energy is equal to the work done by the surroundings, where delta E system equals W surroundings plus Q, where both W and Q are zero. Delta E is also equivalent to delta K plus delta UG plus delta US where delta K equals 1/2 mv squared, delta UG equals mg delta Y, and delta US equals 1/2 ks squared, where S equals L minus L naught. Systems and surroundings. For this lab, our system is the spring, the mass, and the Earth, and the surroundings there is nothing. The initial tracker conditions. The initial conditions were the position was at the negative 0.116 in the x, negative 0.639 in the y, and 0 in the z. The velocity was 0 meters per second, and the object's mass was 0.402 kilograms. The experiment's results. From the tracker analysis of the video, we get these graphs which show the position versus time in both the x and y directions. Now, the graph shows smooth periodic oscillations that repeat nearly constant, but the variation could be due to energy lost or some human error in the tracker data points. Coding. Using the formulas from earlier and plugging them into the GlowScript code, we are able to solve for the unknowns. And from the initial videos we were given the values of M, KS, and L naught. Coding results. This is the image of the modeled version of the video, which shows an almost identical version to the motion that we see in the video. Comparing the results. Comparing the experiment in red to the model in blue, we can see that in the x direction and in the y direction, that both are similar to the expected results, with a little bit of deviation due to some possible errors. Possible sources of error. When conducting this lab, the possible sources of error include human error in tracker and drag and other types of energy transfers that were not accounted for. Discussion questions. Is the energy principle satisfied? Yes, the energy principle is satisfied because the change in energy, delta E, equals zero. This is because the system is a closed energy system, meaning that no energy is gained or lost. Now, this graph from the computational model helps us prove this. Estimates of oscillation periods, where T equals 2 pi times the square root of M over K. Now, using the X position, we're given that T equals 1.6 seconds. Using the Y, we're given that T equals 1.48 seconds. Now, comparing the two, we find the period is shorter using the Y position, but both estimates are very close. So, in conclusion, the energy principle is satisfied since the change in energy equals zero. The experimental data is very close to the computational model, and the oscillation period is shorter using the Y position.